All right, so in this video, we're going to talk about permutations, okay? Permutations is putting things into order, all right? And we'll go a little deeper into that later on, okay? But let's say we got 4 students in a class, really small class. Names are Norma, Rohando, Alex, and Taylor, okay? The teacher knows that one student is always absent, but doesn't know who that's going to be on any given day until class starts, okay? So that means 3 students are going to be in the class every day. All right, so the teacher wants to determine how many different ways, how many different orders the 3 students could walk into the room, okay? Again, remember, we don't know who's going to be absent, so it could be any 3 of these 4 students, all right? So one thing we could do is make a list, all right? So this column says Norma comes in first, and then it's all the different orders for Norma coming in first. Rohando, then Alex, Rohando, then Taylor. Alex and Taylor, Alex and Rohando, and so on, okay? This column is for Rohando coming in first, and then 2 of the other students coming in after. Notice that all these are different orders. Third column is Alex coming in first, followed by 2 other students. And the fourth column is Taylor coming in first, followed by 2 other students, okay? So you can see there would be 24 unique ways that those 3 students, that 3 of those 4 students, could walk into the room, okay? If the number of people is small, kind of like this one, we're only talking about 4 people and only 3 coming into the room, making a list makes sense, okay? But what if there were 20 students in the class and only 2 were absent every day, okay? That means I would have 18 columns of individual students coming in first, 20 columns of students coming in first, and all the different orders of 18 people. That list would take forever to make, okay? So there's an easier method. We're going to do 2 things here in this video. One thing is we can use the fundamental counting principle. And if you think back to the problems we did with the license plates and passwords and other things like that, okay, there's 4 options for who walks in first. So that's our first number here in our counting principle method, okay? After we know somebody's walked in first, that means there's 3 different possibilities for who could walk in second. And then finally, there's 2 possibilities for who could walk in third. Okay, so 4 times 3 times 2 gives me 24, and I don't have to make this list, okay? So the notation you use for permutations is this P here followed by parentheses. The first number here is going to be the number of objects, or people in this case, that are in our group, followed by the number of people that we're actually grouping together, okay? So what this says is we're going to find the permutations of 4 objects when we're grouping 3 of those, okay? So the permutations of 4, 3 is equal to 24 unique ways that, in this case, they could walk into the room, okay? So that notation again, permutation of n, r means n objects taken or grouped r at a time, okay? A couple conditions have got to be met here. Order matters, okay? With permutations, order matters. In the following lesson, we're going to do combinations. And combinations order doesn't matter. It's just being part of a group, all right? So in our example, we were determining the different orders that students could walk into the room. Okay, notice that NRA, Norma, Rohando, Alex, is different than Norma, Alex, Rohando, okay? Because order matters, these 2 groupings, or these 2 sequences, are different, okay? There's no repetition of objects or events allowed with permutations, okay? In our example, Norma can't walk into the room twice. There aren't 2 Normas, all right? So there's no repetition of objects. And permutations are an arrangement or sequence. Understand we're arranging or ordering objects or events, okay? So in this first example, we're going to use the counting principle, just like we did with the license plates problems, to kind of answer these, all right? So let's say instead of having 4 people in the class, let's say we've got 10 students in the class, and the teacher knows that 3 are going to be absent, okay? So our notation, permutations of 10 objects, and we're grouping 7 of those. Notice 3 are going to be absent. That means 7 students are going to walk into the room, okay? All right, so the first student that walks into the room could be 10 different people. And then the second student that walks into the room could be 9. Third student, there's 8 possibilities. Fourth student, 7. Fifth student, 6. Sixth student, 5 possibilities. And then the last student to walk in, there are 4 possibilities. Again, we don't know who's going to be absent. We just know that 3 are absent every day, okay? So permutation of 10 objects taken 7 at a time, fundamental counting principle here. There are over 604,000 unique ways that those 7 students could enter the room, okay? All right. In how many ways can you choose a class president, vice president, and treasurer for a school club if there are 20 students in the club? Okay, so notice these offices are unique, okay? President is different than vice president is different than treasurer, and so on. So we're going to be grouping 3 objects together from a total of 20. So my notation, the permutations of 20 objects when we're grouping 3 of those, okay? So how many possible people could be president? Well, there's 20. Once we voted in a president, there's only 19 students left to be voted into vice president. And once we've got both those offices filled, that means there's only 18 students left who could be treasurer. So if I'm grouping 20 objects, 3 at a time, that means it's 20 times 19 times 18, which is 6,840 ways that we could fill these 3 offices, okay? Number 3, 8 runners in an Olympic final. How many ways could they win gold, silver, and bronze? Okay, so this problem's a lot like this one. Gold, silver, and bronze are different. So winning a gold is different than winning a silver. All right, so my notation, probability, permutations of 8 objects taking 3 at a time. There's 8 different people who could win gold. Then there's 7 different people who could win silver. And then there's 6 different people who could win bronze. All right, so in that Olympic final, there are 336 different ways that runners could finish first, second, and third, okay? And then finally, you've got your 5 favorite books on your desk. How many ways could you arrange those? All right, so in this case, we're grouping all 5. We've got 5 objects, and we're gonna arrange or group all 5 of them. So the permutation of 5 objects taken 5 at a time is going to be 5 times 4 times 3 times 2 times 1, or 5 factorial, all right, which gives us 120 different ways we could do that, okay? So that's using the counting principle. Now, as we go forward, we're gonna use the formula. Let me get down here, okay? So you need to kind of memorize this formula, and I'm gonna show you how to use this formula in a calculator, okay? So the permutations of n objects taken r at a time, the formula is n factorial divided by the difference, okay, n minus r, factorial. So note this is in parentheses, so order of operations still applies, okay? So we're gonna redo number 1 using the formula. So remember, in number 1, we had 10 objects. We were grouping or arranging 7 of those, okay? So when I plug that into the formula, I've got 10 factorial over 10 minus 7 factorial, all right? So that's 10 factorial over 3 factorial. And remember, we simplified these in class recently. That's going to give me, I want to rewrite 10 factorial as 10 times 9 all the way down to 3 factorial. That way those 3 factorials can cancel out, okay? So if you'll notice here, this is exactly what we ended up with when we did the counting principle, all right? You might think, well, why am I using this formula? Because I can just use the counting principle, and that's true, okay? But understanding this formula, and then when I show you how to use the calculator, we just need to understand how those go hand in hand, all right? So we get the same answer, just get to it a little bit a different way, 604,800, okay? I'm gonna go through these last 3 pretty quickly, all right? 20 objects arranged 3 at a time, okay? So that gives me 20 factorial over 17 factorial. Write it out so we can simplify, okay? The 17 factorials cancel out. And again, I get exactly what I did using the counting principle. That's why it works, all right? And that's how we got the 6,840 ways, okay? Last 2, again, I want to go through quickly. 8, I'll spend a little more time on, okay? 8 objects taken 3 at a time, okay? 5 factorials are going to cancel out, and I get the 336 ways again for the Olympic runners to win gold, silver, and bronze, all right? Now 8's a little different. That's why I want to spend a little more time here, because notice in the denominator, when we're grouping or arranging all the objects that we're dealing with, I end up with 0 factorial in the denominator. Okay? And you should remember from our recent work that 0 factorial by rule is going to be just 1. Okay, so again, that's how we got this numerator here when we were using the counting principle. All right, so again, that's how we got 120 unique ways. All right. So you need to know the formula. Let me scroll back up here. You need to know this formula. When we go over combinations, that formula is a little more complicated, and we can't solve combinations problem using the counting principle. So it's good to familiarize yourself with this type of formula, and then I'm going to show you how to use the calculator to evaluate this formula. Okay, so that's permutations.